All right. Morning, Bob.
Yeah, hi.
Oh, there's Vladimir. Okay.
Yes, good morning. I missed you guys very much.
Yeah, I didn't see you yesterday. I was wondering.
Not only yesterday, I was in a vacation for 1 week in mountains with unstable internet connection. That's it, simple like
Oh,
this.
bum.
I
All
came
right.
back
Well,
only, I came back yesterday evening. That's it, simple like this.
all right. Well, good. I'm glad I was getting worried.
Oh, I am glad that to see you and to talk about space.
Okay. All right. So today, good morning, everybody. I'm here. My name is Harry Ricker, and this is the Cosmology discussion group for November 9, 2025. And I'm going to give a talk about space. I talked previously about time, and so I thought that we'd talk about space. Space is a lot more complicated, and we'll see why. Time seems to me to be pretty straightforward. I guess people will disagree with that. But compared to space, we'll see how much more complicated that is. And then that's kind of an introduction to cosmology, which uses general relativity as a geometry of space. And
Oh,
that method is derived from Rene Descartes, who was an inventor of the method of coordinate geometry. I'm going to briefly mention that, and then Bob's going to talk about Descartes, so we'll know a little bit about him and his cosmology. He did have a cosmology theory, and it was later, well, I don't know, you would call it a theory in the modern sense, but he had some ideas. And then that was later superseded by Newton's approach. We'll talk about that. All right, so I guess I need to get going. Um, okay, is that working?
Yeah.
Again, you might maximize it to slide view.
All right, there we go.
That's it.
Slideshow. Is that good for everybody? What is
Yes.
space? I'm not going to try to explain what is space. I'm just going to kind of present what the issues are, the questions that kind of come up. And I'm going to say space is unquestionably the most significant conundrum of modern physics and society. I guess that's a philosophy. Philosophy. It's been discussed for many, many years. It is more complex than time because of the many questions that it poses for physics and ultimately cosmology. I'm going to talk about that. The simplest definition of space in terms of modern science is space is simply geometry. I mentioned that earlier. General relativity views space as geometry. Okay, so what is space? Definitely, I'm going to give some of the things that we can use to define space, and I guess the simplest one is
Sure.
space is where physical things take place. Well, that's kind of vague. What's a physical thing? Physical things are actions such as bodies moving, motion of bodies, planets, galaxies. Then we have particles, fields. That's probably not a
Collisions,
compre. Excuse me.
collisions as well.
Well, that's under um, things that happen in space. Places. So space really involves the idea of place, and that's kind of Aristotle talks about place, and when he talked about place, then later people that got into that. That's kind of a controversy. I'm not going to talk about the philosophical controversy through the ages, but I think one of the characteristics or one of the things is that we have persistence in place of being or existing or existence of material bodies. So we know that planets, our Earth exists in space, we exist in space, and fields exist in space, such as gravity, electricity, and magnetism. So um, material objects, such as ourselves, exist in space, and gravity, electricity and magnetism in fields. So space is involved in this. We also know that involves transmission of forces between different places, such as gravity. So we know that the sun supposedly attracts the earth, at least we believe it. Electricity and magnetism, we know those are forces of attraction and repulsion. And we also know that electromagnetic waves can propagate through space. And we also believe there are such things as gravity waves. Now, there's a number of issues regarding the nature of space that have been brought up. Is space substance or not? Is it something or is it nothing? And then this is the terminology that people will use. They said full space. Space is a substance or a something. And then there's the other idea, which is void space, which it's nothing, empty, nothing, nothing there. This controversy started, I guess you could say, with Aristotle. He was in favor of the full space notion because he said a void was impossible. The materialist Democritus and Leucippus, prior to Aristotle, had argued that what existed were atoms, and they moved around in the void. And the atoms were thought of as being fundamental particles of matter. And the word atom means uncuttable. So that meant that it was the fundamental substance. That's not the same word. That we don't use the word the same way today. So be careful about that. Then we have the question of, does space have discrete parts or no parts? Is it continuous or discrete? Now, I think this is kind of also an argument that's been carried on since antiquity. It's also kind of a modern thing in that, of course, Jim maintains that space is discrete, and there's no such, and the basic mistake of modern physics is it assumes continuous space in time. So that's an ongoing argument. Does space have properties or qualities or no properties at all? So this word quality, it comes from Aristotle, and it's been around for a while. We don't really use that word anymore in modern. We would talk about properties. I'm not sure we know what that word means. I'll talk about that later. So does space, I'll talk about the properties. Does space have properties that which change with time? Okay, I think this is really kind of getting to the point of what I really want to talk about. And that is, we have the cosmology that says space is expanding. Well, what does that actually mean? What does it mean to say that space expands? Well, that implies that size of space is a property, and that's a property that can expand or change with time. What does that really mean?
I think you might clarify there that some cosmologists assert.
Well, that's a standard argument today. So I don't know. Okay, I'll grant you the point. Okay, now the other issue is with Einstein and special relativity, we have the notion that space changes with time with respect to motion, which would be relativity. There's a contraction of space idea. And of course, general relativity says that mass changes space, and energy contained in space changes space, because mass and energy are supposed to be equivalent. What does contraction of space mean? So we talked about expansion of space in cosmology, and general relativity and special relativity. They talk about space contracting. I'm not sure what that means. Does motion change space or merely place in space? Okay, well, that's kind of another way of talking about Einstein's special relativity. How does motion change what space is? That seems like a very peculiar notion. So we have these issues. These are all issues about space, and they're not simple issues, I don't think. Okay, then we have properties of space. What's a property of space? That's a good question. Does space have a shape or size? Okay, well, that kind of goes back to what I was talking about earlier. If space is contracting or expanding, doesn't that imply that space has some property of size or some property of shape? This is dealt with in relativity and general relativity through what's called the metric. We heard a lot about the metric yesterday, and scientists sort of give space a property of distance, which kind of implies shape or size, expanding or contraction. Something is that a property that changes, okay, and at that change is described by, or the size of space is described by a metric. Okay, that's what a metric is. Metric is a word that it implies measure. It's a measure of spaces. He didn't really explain that yesterday. He was talking about metrics and didn't really explain what a metric was. So you really pretty much had to know that to understand his presentation. Okay, we have the other property that we know about. Is this a property? Space has the property that it transmits electric and magnetic fields, gravity, and allows motion. Okay, so it's not a solid. We wouldn't say space is a solid. And one of the interesting things about this is in the 17th century, at the Italian Academy of Experiments, they did experiments where they created a vacuum and discovered that magnetism was transmitted through the vacuum. Okay, so that is how does magnetism transmit its influence through a vacuum if a vacuum, according to these people, is a void? It's a nothing. So how can a nothing transmit electric fields and magnetic fields? So apparently there's something more to space than having the property. So if you take the property of material, things in space, if you take that away from space, space still has the property of transmitting gravity, electric fields, and magnetic fields, and that sort of thing. So how does that work? Our permittivity and permeability properties of space. I think Ian would like this idea. And some people argue that this is the case. I can be persuaded that this is the case. I would think so. I tend to think this is a reasonable view and agree with it. Then in quantum mechanics, you would think there'd be void space, but in quantum mechanics, they say that there's this thing called 0-point energy. And if space is a nothing, okay, it's a void, it doesn't have any properties, it's not supposed to do anything physically, you would think. It's just physically passive. How does it have this 0-point energy property? That's a good question. Then we finally, that's an issue. Is space do these things actually have meaning? Space is quantized. What does that even mean? All right. So those are all issues. We can talk about that. That's something for people to talk about. Then we got the ether problem. Well, I've talked about the ether problem kind of previously because a lot of people say that the properties of space are due to ether that exists in space. So we can give space properties by putting something into space, which people think of as ether. We put this ether in space, and now we can explain these properties of space. Okay, so does ether exist as a property of space? or is ether a property added to the space by something that is put into it that's material? And that's the traditional thought of ether is, and there's a lot of theories and discussion about what this added something is. And there's all a bunch of people with different theories and like to discuss this. Does ether result from matter added to space? As Maxwell had an ether idea where he had invented these electric particles, and he had gear wheels. I don't know if anybody's seen any of the pictures about Maxwell's gear wheels. And basically these mechanical objects that he postulated that existed as ether in space caused electromagnetic waves to be propagated through space. The other idea, and this was mentioned yesterday, is that ether is the fields that exist in space. So in other words, ether isn't a material thing or particles, it's fields. Okay, that's Peter Beckman has proposed that the ether is explained around the Earth by the gravitational field of the Earth. So this is another way of trying to account for something that's in space that gives space its properties. But I think, as I pointed before, there's kind of a question of if gravitational fields allow the transmission of forces, then what property of space accounts for the gravitational fields having the property of doing this? So it's kind of a tautology, if you will. Is the ether a structural particulate substance formed by the action of gravity? So what we're thinking about there is some people think that the gravity kind of pulls all these ether particles together and gives density around the planets. And that would be kind of involved in, well, anyway. Then there's the final question: has the existence of ether actually been disproved? I think mainstream thinks that, but dissidents don't really believe that. So this is, I think, an ongoing question. What is there an ether? Is it something that is added to space in addition to space? It exists in space in addition to it, and this explains the properties that I talked about earlier. Okay, but then you have this tautology or circular argument of, well, if the gravitational field is responsible for the propagation of electromagnetic waves, okay, then how is gravity transmitted in space? So it's kind of leads you to a circle of questions. Okay, this is a kind of a traditional argument, absolute versus relative space, and this goes back to Newton and Descartes, which we're going to talk about. Bob's going to talk about later. This is discussed in the I forgot the name of the book now. That's darn. The Clark-Leibniz correspondence, I believe. And Leibniz took the position that space is relative, and the defender of the Newtonian point of view is that space is absolute. I'm not really sure this is a well-defined problem, and I don't think it's really relevant to us anymore, but it's of historical interest. And my main question is, I don't really think absolute versus relative space is as meaningful as the modern problem, which is, can space change its size? Okay, it's expanding and contraction. That's kind of the modern thinking about it. And then we get to this issue of What does that mean for relative versus absolute space? I think this is kind of a muddled issue, is my point. For Newton, absolute space meant the fixed space of the sun. So what Newton was talking about in absolute space was he was trying to define a cosmology, okay, where the sun was at the center of the universe, and and that was defined as absolute space. And then he was talking about relative space as the space we experience on the earth as we're moving around the sun. So he was trying to make a differentiation between absolute space and relative space to sort of explain how it is that the earth is moving around the sun, and why is it that we seem to experience space in the same way that the absolute space exists. And so what he said was that relative space is a copy of absolute space that can be moved around the sun. Now, that's a very it's a simplification, I would say. And Newton was really trying to justify the Copernican system, I think, is really what that boils down to. And it's kind of hard to, if you're doing mathematics, you need to have a defined coordinate system. So absolute space, I think, defines a coordinate system, and Newton needed this absolute coordinate system to do mathematics in. So if you define your coordinate system with respect to the sun, then you can do Copernican mathematics to explain the motion of the planets around the sun. Okay. Now, today we also have an idea of absolute space where we say in cosmology that the absolute space is defined by the cosmic microwave background. So this idea still exists in modern science. Okay. Then Newton defined absolute space as the same figure and magnitude. So fixed, immutable, and unchanging. So Newton wouldn't have, he would have said this idea of space changing its shape and size, it doesn't really make any sense to him because his space is mathematically uniform. So you have a coordinate system. The coordinate system, the units of distance in the coordinate system are not really changing. They're fixed and immutable. And I think that's the important point. And if you're going to do mathematics, you kind of have to have you're going to prove things by mathematics. You have to have a reference system of coordinates that is defined and fixed and doesn't change. If your coordinate system can change, then how can you really prove anything mathematically? Okay, I think that's the point there. All right, now we're going to talk about the geometry. So I've already introduced this idea of the absolute space. And we're measuring space is geometry. We use geometry. That's the mathematics that's used to measure space. Now, this goes back to Euclid. And I think the best way to view Euclid is he's summarizing the existing knowledge. And so I think he puts together a compendium. And in that compendium, he makes this assumption about points. He uses the notion of points and lines and planes. And these points are infinitesimally small things. And it doesn't seem like they can really exist. They're not really physically anything, I think. And we'll find out this causes a problem later. And so points are idealized concepts, these point lines and planes. And the lines consist of points, okay? And they're infinitely small. So, infinitesimally small. And then you have planes, and planes are infinitesimally thick. And then you have volumes, and volumes are filled up with these points. Now, this is really a problem, and it crops up later in mathematics. And so that's an issue. We have the issue about infinitesimals in geometry and in mathematics. And then the other issue that we have is that in the 19th century, the parallel postulate was disputed, and so the argument that there's only one line parallel to a line through a point that got disputed. And so what that means is that you can construct multiple geometries. And if you have multiple geometries, that means geometry isn't unique, which means your measurement of space is not unique. Okay. Is before you can really measure it. That's kind of a problem. Okay, now we're going to get down to Descartes. Descartes initiated modern geometry with his analytic geometry. Okay, so what Descartes did was he changed the Euclidean geometry, which dealt with figures, points, lines, and planes, and you did proofs, by drawing pictures and making comparisons. So you did proofs by drawing pictures. Analytic geometry has to do with you assign points in space to be numbers. So you define a coordinate system. We should all be familiar with this. And then you define, assign a number to a place in the coordinates of space. That's the basic idea. And it's the primary tool that's used in general relativity. Okay, and I'm going to talk a little bit about Einstein. General relativity has space-time coordinate system that is changed by motion, mass, and energy. Okay, so what general relativity is telling us is that if we have a coordinate system, okay, that's basically the Descartes idea, where we assign numbers to places or points in space, okay, that this coordinate system, as I discussed earlier, Euclid had the idea that space was Euclidean. We call it Euclidean space, which means that height, width, depth, those ideas are orthogonal to each other, and the coordinates are kind of immutable. So in other words, a distance everywhere in space, the distance represented by numbers on the coordinate system are the same everywhere. That's what Newton meant by immutable. Because you didn't want the coordinates to be changing with distance in the coordinate system, and you wanted the coordinates to be independent of anything in space or any other physics. Okay, that allowed Newton to use mathematics, the mathematics that he knew, and he invented calculus with Leibniz. And so that tells you that the mathematics that they were using was really simplistic algebra, and then they needed calculus, and calculus sort of evolves out of so anyway, my point that I'm making is that the assumption basically is that the coordinate system is immutable. It doesn't change. So if you say that, then you can do calculations, you can create a geometry, and you can prove things. And I think that's the basic idea that Newton was operating on. Okay, but now, okay, and we say that motion can change the coordinate system. That's what Einstein supposedly said with special relativity. So motion, so an observer in motion relative to another observer in a different inertial frame, their coordinate systems, how are they measuring space and how they're measuring time, they're not the same. And this is kind of a problem, I think. All right, so measurement of space, that's because measurement of space is based upon light. So space is measured by light. Now if we're talking about measuring space by light, we have to have a geometry that represents the measurement of space by light, and that's what we have today. Okay, the philosophical problem is, does this mean space changed or merely its measurement? Okay, so if we're measuring by light, then is that really representing what space is, or is that just representing how light acts in space? Okay. Modern concepts regarding curved space and expanding space cosmology seem to me to be kind of fanciful. I mean, you're talking about space changing and time changing, but all you really mean by saying those things is that when you do measurements by light, you get different results. Okay, so does the universe expand? Is the expansion of space in cosmology real or merely a convention? Well, I don't know what the answer is to that, but I think it's more of a convention. It's something that people believe. Can we detect the difference between expanding space and non-uniform progression of time? I don't think you can. So if you say space is expanding, how can you know that? Maybe time has changed. So what we're measuring as changes in spectral lines, maybe that's because time is not progressing at the same rate now as it was previously when the signals were emitted. So I think this, I don't think we can really answer that space is expanding or not. I don't think we can really know that. So can cosmologists tell us which cosmological model is correct, given the many different geometries of space that are possible? Okay, so this is another issue, which is you have a lot of different possible models. I talked earlier about that geometry is not unique. So when they discovered that geometry is not unique, that meant you have to figure out what the correct geometry of space is, the correct way to measure space before you can measure it. Okay, so what they do in cosmology is they assume that there are a lot of different possible models, and then they make measurements, and they try to figure out what measurement matches the model, the different geometry models of space that are possible, and they try to figure out what the correct geometry of space is based on comparing measurements against their model predictions. So that's what cosmologists are doing. That's kind of the reason I'm talking about this. Okay. So I'm going to try to end up here. In modern science, we define space based on how it is measured. I tried to explain that. We have to assume a geometry, a model of space, and then try to compare that to measurements and decide what's the correct model. The measurement method depends on the assumed geometry used for measurement. So yeah, you have to have a model of what space is before you can measure it. Well, and that's kind of complicated. That's a theological issue. The science of geometry produces many different geometries. So this problem doesn't, we can't just assume Euclidean geometry is correct and then say, well, that's the correct geometry of space. It turns out, since they discovered that geometry is not unique, then we can't do that anymore. What space is physically is a matter of dispute. Okay, then there's the ether problem that involves the ether problem. What is ether? And then you have all these different theories about the ether. And there's lots of arguments in the email discussion groups about that. It seems that cosmology cannot definitely answer what the geometry of the universe is. Okay, well, it's kind of ambiguous. All right. Now I'm going to, that was my summary of space. Now I'm going to kind of talk about Descartes. I'm moving through this pretty quickly. And hopefully Bob will talk about this a little in more detail. Main point, he's the originator of modern philosophy. And that's what books will tell you. And his approach is this rational mechanism. You know, things are logical. can be proved logically. We can understand the universe through thought. And he has a mechanistic assumption about how things work. And it's kind of peculiar because he's a Catholic, and his cosmology starts with God willed the universe into existence. That's interesting. The world is rational and comprehensible. All laws universal and derivable from one basic law. This sounds familiar. This is like the physics searching for the one physical law from which all physical laws can be derived. Well, that comes from Descartes. And this is kind of interesting. The task of science is to create utopia. He believed that scientific knowledge would make everything wonderful for human beings. This is something that I knew that I hadn't really fully appreciated. He came up with Newton's first law of motion. Okay, so he was the first one to enunciate what we call Newton's first law of motion. Newton didn't come up with the first law of motion, Descartes did. Then he invented analytic geometry. We talked about that. We call coordinates, people, when they talk about geometry, general relativity, they talk about Cartesian coordinates. Okay. And then there is no void space. Descartes didn't believe in empty space or void space. He believed that space was full, that there was something. And I think this is kind of interesting. He had this vortice idea that space was spinning around, and so he had vortices that explain planetary motion. He also had vortices to explain magnetism. Okay, so I got about 2 minutes left. I went through it pretty
Just a
quick.
very quick observation, if I may. We talked last time about simultaneous discoveries and so on. And you mentioned Leibniz and Newton, but actually, analytic geometry was invented simultaneously, it is believed, by Fermat. Descartes is normally given the credit for it. He talked about Cartesian coordinates, but I think Fermat also developed the concept of applying algebra to geometry.
Yeah, I can't talk to that because I'm just going by what the standard books on Descartes say. And this phenomenon of attribution of discoveries, that's controversial. And, if you get into the history of science, and so you're probably correct. But, the story is that Descartes was in a room in Germany, and suppose the name of the room was an oven, which I don't really understand that. But anyway, apparently these rooms were small. And he saw a fly flying around the room, and he thought, oh, I can describe the fly flying around the room as with numbers relative to the walls of the room. So he had a ceiling and walls and a floor. And so his idea was to describe the motion of the fly with numbers relative to the walls. That's the story that they tell. Okay, we got less than a minute. Any other quick comments? All right, I'm going to let Bob talk in the next session here. We should be cutting off here soon.
Good presentation, Harry.
I'm trying to find the end thing. So I cut it off. Well, thank you, Jerry. I don't know. I just was trying to make a quick summary. That was really my objective. Kind of introduce the issues and sort of put in perspective some of the discussions. Struggled. I mean, when I turned on Zoom, it just took forever for it to bring up the activate the Zoom program. Okay, so Bob,
Yeah, okay. If you can send me a request. Let's see.
No, you send the request.
Okay, let's see. Send request. Okay.
I noticed we have a new participant, James. I wonder who that is.
That's probably James Aratoon. Just guessing.
Yeah, it's me.
Yeah.
I'm just,
Hello,
All right.
James.
Well,
I've just got a
welcome.
slightly sore throat. That's all. So.
All right, Bob, you're on. We can talk a little bit more about Descartes. And
Okay.
I've already talked about Descartes. And so go ahead, and then we'll ask questions later. Do the
Yeah, okay.
slideshow thing.
Okay, let me see. Slideshow from beginning. Okay, yeah, there's my website, quantumrealism.net. And if anyone wants to look at my system, it's kind of speculative, but quantumrealism.net. And actually, it has a fair amount in common with Descartes. Not everything, and maybe I'll get into a little bit of that. But in any event, talk about Descartes. Yeah, I've known about Descartes for a long time. My background's philosophy. He's often called the father of modern philosophy. There's a lot of truth there, but to some extent, maybe you could even call him the father of modern science. At least he's a major contributor. And you can tie all of this in with the Renaissance, where there really was a rebirth in a lot of fields. And Descartes explicitly says that he's trying to give both philosophy and I would also say science a new beginning. To what extent that's true, again, I think you can either overstate it or understate it. But in any event, here are a list of his books, Rules for the Direction of the Mind. Some of these were in Latin and some were in French. When he was trying to be on the good side of the Catholic Church, he tended to write in Latin. When he was trying to get on the good side of the common people and get around the church, he tended to write in French. His first work, major work, Le Monde, or The World, or this was in French, but Descartes did not publish it, at least during his lifetime. And the reason was because of what happened to Galileo, who was put under house arrest, and Descartes didn't want to have the same thing happen to him. And it was highly speculative, but among the things that he says is that he agrees with Copernicus that the sun is the center of the solar system and not the earth. He takes that back a little bit in his Principles of Philosophy, but in any event, that was considered a heretical opinion. So Descartes tried to get around this a little bit more with his Discourse on Method, that's actually the introduction to three works on science: the meteorology, the dioptics, and the geometry. Then we have his meditations, which were written in Latin. The Discourse on Method is quite similar to the meditations, and these were published together with the objections and replies. Among the objections and replies, one that I find particularly interesting is the fifth series of objections and replies, and that is with Pierre Gassendi. It turns out Descartes, for example, opposed the atomic theory, but Gassendi supported it. Also, Descartes, he was a dualist. Actually, I'm also a dualist. So he makes a sharp distinction between what he calls res cogitans, which is a thinking thing, kind of like the human soul, and res extensa, which is a physically extended thing, which he basically identifies the physical universe with. And Gassendi questions whether Descartes should have been as negative as he is about res cogitans as being spatially extended, because Descartes includes, the thinking thing, he includes perception within it, and that presumably is going to include visual perception. Visual percepts, pretty obviously, are spatially spread out, and Gassendi pushes that a little bit with Descartes. Then we have the Principles of Philosophy, which is quite similar to Le Monde. I gather was basically written as a textbook, And finally, Passions of the Soul, which is his position on the mind-body problem. This was in French. He also had a correspondence with Princess Elizabeth of Bohemia on the mind-body problem. And Descartes had an interesting argument that the mind basically interacts with the brain in just one point in the pineal gland. And his argument was most parts of the body come in pairs. You have two eyes, two ears, two lungs, two kidneys. But there's only one pineal gland, and also there's a certain like convergence of nerves into the pineal gland. So that's where he claimed that the body and the mind causally interact. Let's see, Descartes' method. If you just read the meditations, and unfortunately a lot of people in philosophy, they just read the meditations and they get from this, and Descartes does say it, that you can only accept something if it's known with absolute certainty beyond any possible doubt. And then he gives his famous argument from dreaming that how do we know at any given moment that we're not in the middle of a very realistic dream? And he says we can't know this with absolute certainty. So Descartes, being a dualist, he does think that there's a physical world out there, but at least in the first meditations, and actually all the way into the sixth meditation, he doesn't think that we can have knowledge of that world. But the real truth is Descartes, in his contributions to the sciences, like in Le Monde and in the Principles of Philosophy, as far as I can see, he doesn't insist on absolute certainty. He bases a lot of it on observations. In his contributions to optics, for example, he did dissections. He looked at the back of the eye of an ox and saw the retinal image. And he did do at least some experiments in physics. So Descartes is classified as a rationalist, where you say that all knowledge is based solely on reason. So you talk about the continental rationalists like Descartes, Leibniz, and Spinoza. You read Spinoza, it's almost like Euclidean geometry, a series of postulates and then various deductions. And I think that is kind of true for Leibniz and Spinoza, but I think it's less true for Descartes. And those who make the distinctions, on the continent, you have the rationalists, and on the British Isles, you have the empiricists like John Locke, Bishop Berkeley, and David Hume. Also, in his rules for the criterion of the, rules for the direction of the mind, he has the principle of breaking problems into separate parts, which is a good principle, used in computer programming, among other places. And it's also his criterion of being clear and distinct, where being clear is that which is present and apparent to an attentive mind, and distinct, that which is so precise and different from all other objects that it contains nothing but what is clear. Okay, so Descartes, he doesn't want to, he wants basically to avoid error, and the way to avoid error, I guess, is to be as certain as possible. But I think, again, that you can overstate this in saying that he always insists on absolute certainty. That's his method. Let's see if I can go back. Paradigm shifts that were made during the Cartesian revolution in science. The first is a shift from the teleological, in other words, in terms of purposes, entelechy, that's the technical word, or telos here, of Aristotle. For example, an acorn becoming an oak tree, that's its ultimate purpose, is to become an oak tree. And the shift is to mechanistic explanations. And these occurred with the, well, Lucretius he was a Roman, he had a book, De Rerum Natura, the nature of things. And that was lost for a long time. But a single copy was discovered in 1417. And this led to the revival of the atomic theory. But you have to be careful. I mean, you'd think atoms would fit in nicely with the Descartes system, but he himself rejected the existence of atoms because he thought that if they involve extension, that at least in principle, extension always has to have parts, and in principle, you should be able to divide the parts, in which case the atoms would not be indivisible. You come across that principle actually several times with Descartes, also with Hume. That which is spatial, it's distinguishable, and what is distinguishable is separable. And I think probably what the lesson maybe to learn here, because Descartes uses that to say that the mind is not spatial, maybe the real lesson to learn is that there's a problem with the principle. Okay, but the second shift is from Ptolemy's geocentric system to Copernicus's heliocentric system, from the Earth-centered system Ptolemy with all his epicycles and things to Copernicus's heliocentric system, which also has a few epicycles. Descartes, at least in the principles, he's somewhat sympathetic with Tycho Brahe's compromise system, where the Earth is the center of the solar system, but all the other planets, they revolve around the sun. I gather in Le Monde, he actually is completely sympathetic with Copernicus, and whether he tries to reach a compromise to get on the good graces with the Catholic Church, I think is a good question. Vision, there's.
I think sorry, Robert, I think he was also quite orthodox in his views. He was, totally acceptance of the Pope's position, and he was probably trying to reconcile his own strong views that the Roman Catholic Church was infallible with his, acceptance of the Copernicus heliocentric system.
You may be right there, Ian. He certainly claims to be a Catholic. He was educated by Jesuits at La Flèche in France. To what extent he was going through the motions and to what extent he wasn't, I think is a good question. Certainly in the Meditations, he gives like two very well-known proofs for the existence of God. But I have actually run across at least one person who claimed that he was a closet atheist. And so it's kind of difficult to actually sort things out, because certainly the church had a lot of power during the time. But so I don't know if I even have a strong opinion there. Okay, but in vision, and certainly Descartes contributed to the theory of vision. Actually, the one who discovered how a lens works was actually Kepler, kind of a contemporary of Descartes. But there's a shift from exocentric systems, which actually even Euclid held in his optics, where it goes from the eye to the object, as if the eye almost like has little feelers that reach out to the distant object by means of which we perceive. To an endocentric system from the object to the eye. And of course, like once Kepler discovered how a lens works and the discovery of retinal images, then it seems like vision works by the other way around, with the passage of light to the eye and then something happening in the brain, and something like a reconstruction of the distal object occurring in our mind. And Descartes, there's a controversy with the law of refraction, whether it was by Snell or Descartes. Certainly Descartes uses the law of refraction. I have a diagram on that in a second. There's also a shift in geometry from just working with ratios, as Euclid basically did, to analytic geometry. As far as I know, it was Descartes who came up with this. And certainly the coordinate system is named after Descartes, Cartesian coordinates. Yeah, I've heard Harry's fly story before. Yeah, the fly moves around. I heard it in terms of little squares on the ceiling. But yeah, and if you can describe that, each of the squares with a coordinate system, then you can describe motion with an equation, which of course is a very powerful technique. You can describe the curve by solving a series of equations. You don't have to do everything like just in terms of postulates and making various proofs as Euclid did. So that's also a major contribution by Descartes. Let's see. Yeah, here are a couple of diagrams from his dioptics, looking at the backside of the retina. And then, of course, and Descartes even is aware of this problem. There's a danger of a regress. If the person is looking at the backside of the retina and the person has eyes, how does he see? You can keep repeating the issue. And I don't know if Descartes really has a great answer. And also I have a diagram for Snell's law, the law of sines, where with a refracting medium, it changes the direction of a light ray, and then you have the ratio of the two sines, gives you the index of refraction. I should note here that Descartes himself thought that light, the speed of light is infinite, and he thought of it as like a pressure wave. But of course, the modern analysis here talks about the ratio of the two velocities of light. So Descartes' explanation needs a little bit of a patching here, but he was certainly aware of the law of refraction. And of course, the way it works with an image is a refracting medium like the cornea of the eye or the lens. It changes a diverging light cone into a converging one, where if everything is in focus, it converges to a point on the backside of the eye, the retina. Let's see. Okay, here are some of the claims made in the Principles of Philosophy, and similar claims are made in Le Monde. Descartes did not believe in the existence of a vacuum and identified matter with extension. Okay, res extensa, a spatially extended thing. As far as I can see, he was actually also working with the concept of an ideal solid here. And the ideal solids, they fill up all of space. This is this nested series of vortices or spheres. And they are capable of circular motion. And Descartes identifies the circular motion. I think his prime example, it's a little bit like Ptolemy, actually, where like the motion of the planets, they move in the motion as perfect spheres. And of course, this runs into problems like with, well, Descartes was aware that there's a problem with comets, but also with Kepler even, like with elliptical orbits. So those aren't perfect spheres. You can add epicycles, which sounds kind of ad hoc, and as far as I can see, Descartes uses them, as did Copernicus. So you put enough effort, you can be consistent with observations, but sometimes it takes quite a bit of effort. Also for Descartes, all action is taken to be contact action. There's no action at a distance. So you have pushes, like one object, say a physical object, it can, say, collide with another, but there aren't poles. Light is taken to be a pressure wave which propagates at an infinite velocity. I might add here that with the rotation of like these vortices, Descartes talks about something like a centrifugal force. And the centrifugal force, it causes the pressure wave to be propagated. But light itself, according to Descartes, always goes in a straight line, and again, at an infinite velocity. Okay, Descartes doesn't like the concept of the infinite, at least as far as matter or the mind is concerned. His only infinite substance is God. So he tries to patch things up a little bit for the universe by talking about the concept of the indefinite, which is kind of like an epistemological concept, in other words, involving knowledge. For any like a given claim that we've reached the end of the universe, you can always say that it extends still further, but you're not saying by how much. Actually, if you look at Lucretius, he talks about kind of a paradox. If you go to the end of the universe, you could throw a dart, and so it can't be the real end of the universe. So this is also a little bit like the concept. It's given both by Aristotle and also Locke of the potential infinite as opposed to the absolute infinite. With a potential infinite, like you could say with counting, for any claim that we've reached the biggest number, that you can keep going on, you can keep counting. So it's just like potentially, the symbol here is something that's called the lazy eight, as opposed to Aleph naught, which is the actual infinite. And you get paradoxes for the actual infinite also, like with Cantor's work. But for Descartes, there's no real limit to the universe, but he's not saying that it has an absolute and infinite size either. So he has the concept of the indefinite. see. Okay, here's a picture from his system of vortices. You have these nested like rings or shells. There's actually a similar diagram in Le Monde, but this is taking up all of space. So again, there is no empty space. Uh, but you might note that like these are confined to finite regions. Here they tend to be hexagonal in shape. I fooled around with shapes like these, but it kind of raises the question: how are you going to get like a nice coherent model of the physical world if you keep each of these like just like with finite sizes and shapes, finite regions of an area? You can try like having the whole system be enclosed by like a bigger shell or something like that. I've played around with that, and my solution is actually a bit different from Descartes here, but I have to bring in added dimensions. Okay, but that's his system. Okay, Descartes' account of magnetism. I think Harry knows more about this than I do. But he identifies magnetism with circulating vortices around pores in matter. The fact that a magnet has a north and a south pole is explained in terms of the directions. Descartes calls them the windings and uses the word screws here. So you could have a left-handed screw or a right-handed screw. So this will give the direction of the rotation of the vortices. So you can have both the North Pole and the South Pole. And then he thinks of the whole Earth as being like a giant magnet, with the poles of the magnet corresponding to the north and south poles of the Earth. Okay, problematic cases for Descartes' system. Yeah, the first I've already, well, I should sort of mention both already, but the first, shells with different centers will either collide with each other or overlap as they get greater in size. I myself go along with the overlap here. So I have like each charged particle have its own set of shells. But with Descartes' system, where he doesn't talk about parallel spaces or anything like that, like I do, there is an issue about what happens when they collide or overlap. And there's also a problem in accounting for the orbits of bodies with highly eccentric orbits, such as comets. There's a whole section of the principles devoted to the discussion of comets. Descartes makes various moves. He talks about degrees of solidity, for example. It all sounds kind of ad hoc there. He tries to make the work system, make the system work, but most of the patches to me sound kind of ad hoc, which is among the reasons that, as far as I can see, people kind of gave up on this. But okay, here's a comparison of the Cartesian and Newtonian research systems. For Descartes, all action is contact action, no action at a distance. Newton, as far as I can see, he does believe in action at a distance, although he does say also in his principles that concerning gravity is his famous Latin phrase, hypotheses non fingo, where he doesn't make hypotheses. So he maybe more an agnostic attitude. But in any event, for Descartes, fields are construed realistically, and thus a potential explanation is given for changes in bodies in terms of the fields impinging on the bodies. Light is construed as a pressure wave propagated in infinite velocity. And for Newton, he gives a corpuscular theory of light, which is propagated with a finite velocity. And I gather Newton, at least, he was aware of Rømer's work with the moons of Jupiter, is giving evidence that the velocity of light, in fact, is finite. And Descartes was he was writing before that. So you do have to put people into historical context here. In any event, I have a final slide. Possible reasons for the Newtonian research program coming to predominate over the Cartesian one. My concept of a research program, actually, I got this from the philosopher of science, Emery Lakatos, who talks about progressive and regressive research programs, where there's no one experiment that will conclusively refute a research program, since you can always put an ad hoc patch on it. But with a progressive one, you kind of minimizes the ad hoc patches, whereas you have to do this all over the place with the regressive ones. And so I think a lot of people, at least at the time, thought that Newton won out here. His research program was a progressive one, and Descartes was a regressive one. So Newton's program was more empirical, based on observations. As I noted, at least in philosophy, Descartes is classified as a rationalist, but I think this is also misleading. Descartes himself, the historical Descartes, was not anti-experiment, and he conducted experiments. So again, I think you can overstate things. Newton's program was quantitative. There are definitely equations and the principles. In the principles of philosophy, things tend to be a little bit vague. There aren't any explicit equations there. But you got to, again, be careful. Anyone who invented analytic geometry, you can't accuse of really being anti-mathematics. Well, it is true, of course, that Newton invented the calculus also. So again, I think you can overstate or understate this. Newton postulates a quantitative theory of gravity, whereas Descartes did not have a theory of gravity. As far as I can see, they didn't even have the concept of gravity there. And even if you look at Kepler, who of course came up using Tycho Brahe's data, that the planets, their orbits are elliptical. You look at Kepler's metaphysics, it's actually basically Pythagorean, and talk about music of the spheres and stuff like this. Kepler was a very good mathematician, but I think I prefer Descartes' ontology over that of Kepler. And my final point here is, in the 19th century, a local field theory was invented by Faraday in terms of lines of force. And I note some of my own work here, like with my thin shells. If you take in the principle that these have equal volumes of series of thin shells, of nested thin shells, and if you use the principle that each of these has an equal volume, you get an inverse square law right out of this, because the area of a sphere is proportional to the radius squared, in which case its thickness has to be 1 over r squared, and there's your inverse square law. Now, Descartes never says this. He does have his hierarchy of spheres or vortices, but I can't see any place where he actually comes up with this. Whether I'm the first person to or someone else is, I'm not sure. Often what happens, I think we mentioned this last time, people independently come up with the same thing. Okay, so maybe there's something to be said for the revival of some of Descartes' ideas. I don't personally like the idea of action at a distance. I like local field theories or even global field theories. But in everyone, you have to put into historical context. So I think at least some of what I say, probably its basis you can find as well in Descartes as in anyone else. But again, or even as Newton said, that people work on the work of others, and that's true. And so you have to give credit to others when they come up with similar ideas, in particular when you didn't just come up with them independently, but you actually use them. Okay, but in any event, that's the end of my presentation.
Well, that's good, Bob. Thank you for that. I hope we learned some things. I do want to give a little pitch for me, and that is that if we go back to the magnetism slide, I discussed Descartes in my treatise on magnetism, which, if you're interested, you can go to the General Science Journal and look under Harry Ricker. And I have a whole bunch of chapters to a book. I call it a book. There are a series of papers, and it starts off with the Greeks and the Romans and goes through to up to the 19th century, and Descartes is included. And it talks about the different ideas about how magnetism works. And what's interesting is the issues kind of like um, the idea about what magnetism is kind of changes with the fashion of the times. And it seems like we don't really know for sure what magnetism is, but there's a lot of ideas about it. And the ideas have been changing back and forth between magnetism is transmitted by particles versus magnetism is transmitted by some kind of a field thing. Okay, we got about 9 minutes. So anybody want to make some comments or questions here?
Could I make a comment? Both of you didn't mention inertia. For example, whether inertia is a field theory or.
Wait a minute. I pointed out that Descartes came up with that idea.
Yeah, my understanding
Well,
also.
well, Aristotle came up with inertia is a sort of is a concept in the field, but then it seems to have died a death. And Aristotle's ideas where you have a sort of a forward flow, almost pulling the object through the vacuum or through the ether. But I wanted to know whether you've got any thoughts of whether that developed in the Robert in the Descartes, and what your thoughts are, Harry.
Well, one point with Descartes is his concept of momentum is mass times speed and not mass times velocity. So he doesn't have it as a vector concept. So a lot of these ideas, they're kind of evolving, but I do know he says that again in the principles, and so and of course Newton, and I think Newton would be the first to admit that like a lot of his concepts, like the body in motion keeps in motion and things, that he gets them to some extent from where he builds on the work of previous people. So I think inertia was actually an evolving concept. Or I know with Galileo, for him, it's with like it's actually with more circular motion that's primitive for inertia rather than rectilinear motion. So it took people a while to get the modern concept.
Good answer, Bob. I don't think I can add anything.
Thanks. Thank you.
So anybody else? There's Roger. Go ahead.
Hello. So, before Einstein came on the scene, they were trying to form a unified theory of physics based on vortexes. And what I think happens, they were thinking in terms of vortices in the ether. And then when Einstein comes along, they think they can get rid of the ether. So they abandoned looking at vortex theory after that. So that's basically,
Yeah,
that was
I
basically,
talk about this. Go ahead.
sorry.
I was going to say that I talk about this in the books that I referred to, or the chapters of the book on magnetism. I discuss this in where I talk about Newton's theory of magnetism, and you'll notice that Bob mentioned that Descartes thought of magnetism as this vortex, swirling around the magnet, and the swirling around of the magnet caused the magnetic attraction and repulsion. Okay. And that idea got translated into what gravity is, okay, for the Cartesians, if you will, followers of Descartes. Leibniz is considered one of the followers. And Leibniz had this idea that planets are swirl around the sun by the action of the vortex spinning around the sun, the circular motion of a vortex moving around the sun. And that idea, Newton didn't have that idea in his system, and that idea fell away with the acceptance of Newton's viewpoint. But
As
is
far as
that what
I
you want?
know, as far as I know, Descartes never mentions an ether, but he does talk about things being spatially extended or extension. But I think you probably could classify his system as being an ether theory.
Good point.
Yeah, because you got the problem of what is it a vortex in. Anyway, historical interest on the conspiracy side of things. Descartes might have been murdered. Do we
Oh,
aware of
that's
that?
interesting.
Do we aware of that?
I hadn't heard that.
When
He
they,
died in Sweden
yeah,
at the court of Queen Christina, and they claimed at the time it was from a bad cold, and she liked her philosophy lessons early in the morning, and he liked to sleep in and stuff like that. But
yeah,
I don't know, maybe you know something more on this than I do, Roger.
but yes, his friends were supposed to think he was murdered, and it was tied into what they did with Galileo. They Catholic Church had these fanatics who wanted to get rid of heretics. So they can, on the conspiracy side, they think one of these people poisoned him, so it was all covered up. And in the more modern times, they want to look at his body, do a forensic test on it, and that gets refused. So what you just end up with a conspiracy theory, and you can't really test it. So a lot of this science physics ends up with loads of conspiracy theories all over the place.
Okay. Hadn't heard that particular. Jerry, you have any comments?
Well, I had a whole bunch of notes written on the first session that I'm trying to recall. Um, I mean, I expressed a lot last week, I think. Well, as far as, well, it was mostly about time, but I think we talked about space some. That I think space is an empty void, that all physical phenomena and their interactions exist and occur. I think if an ether exists, I think it exists in empty space. I mean, space doesn't expand. I mean, if it were I mean, like, it would have to be physical to expand, and there isn't a curvature. It doesn't contract. With geometry, I would say that it involves shapes with angles and such, and that's drawn, or it's it's in space, whether it's three-dimensional or if it's two-dimensional. Two dimensions can't exist in reality, but also with what was it? I'm losing train of thought. Anyway, yeah, that's a few thoughts.
I would like to say that space does contain one property, and that's cold, lack of heat.
Well, I hadn't thought about
Oh.
that. That's an interesting way of thinking about it. But some people could argue that the cosmic microwave background is an expression of temperature.
I think anything that's cold, like something physical, has to be cold. If it's nothing, there's no temperature. I mean, if you have a thermometer in a vacuum, that isn't the temperature of the vacuum. It's the temperature of the thermometer, for instance.
Right.
That's my personal view.
Well, we attribute heat to.
Interrupted. I'll just say it didn't occur to me to discuss temperature. I probably should have, because it's not really clear to the mainstream view about temperature, or is that the cosmic microwave background is radiation that exists in space. And their theory would be that space is just a background in which the radiation is occurring. And so they wouldn't assign a property of temperature to space. But if you looked at space as being a substance, kind of an ether type thing, then you could say that space has a temperature.
Well, you're defining a convective temperature. So, in other words, if you put a thermometer out in outer space, its convective temperature is undefined because there are no molecules to impinge upon it. But it could be receiving radiation, that's true, from an object or from the CMB, and therefore it would register some sort of radiation reception. But the convective temperature is undefined because that's merely a question of the molecules, the velocity of the molecules hitting the bulb of the thermometer.
Well,
Right.
temperature, I think temperature can be defined as EM radiation and emissions. In space around the planet and in space around the solar system, there's going to be differing temperatures. But I think the property of space is that it's basically cold. It's
cold is perhaps not anything substantive. It's merely the absence of heat, or the absence
cold is the lack of motion.
Of rapid motion of the molecules.
Yeah, that's lack of motion. Cold, you take an atom down here and you put it into space, it's going to slow way down because of it has nothing beside it to help it vibrate. So that
they
makes
don't
space
say that
cold.
if you put a thermometer out in outer space, it will register absolute zero. They just say it's undefined because there are no molecules there. We're talking about a perfect vacuum, and the bulb isn't capable of receiving radiation. So you'd need a receiver for that purpose.
Mm-hmm. I agree. Lack of radiation is temperature. The more radiation, the higher the temperature.
Well, radiation is one form of increasing the temperature of a body. But again, it's indirect because the energy in that radiation would start the molecules in the substance to move at a rapid pace. And therefore, but the kinetic theory of gases, if you accept that. May I just raise another thing? I was going to raise this about the biological ruminations of Descartes. And I think maybe, Bob, one of the reasons why some of his ideas were discountenanced in more recent times was because you mentioned the dioptics, and you mentioned the ox's eye and the analog and so on with the human eye, but Descartes, in as far as I can see, in looking at analyzing the animal kingdom, came to the conclusion that there was a major difference between humans and animals. In fact, animals were just automata. They were just like a machine that you would construct.
Right. There's no res cogitans in the animal, according to Descartes. There's no soul.
I was just going to say that. You've taken the words from my mouth. Yeah. So in modern times, with I suppose the study of naturalism and so on, his ideas would be discountenanced as medieval.
Maybe. I think you find two different directions there. You get the complete materialist who says that there's no res cogitans, which is fairly common. You also get panpsychics who'll say that there's a mind in animals and on almost anything. So I find people making both of those moves. But it is kind of like anthropocentrism to say it's just the human that has the conscious mind. And among others, if you at least go along with evolution, how did that evolve? Whereas the panpsychics, at least they have an answer there. It evolved from a more primitive form of consciousness.
Well, I think the PETA people claim that animals have rights just like humans, and so they would take the point of view that animals have souls just like humans.
Well, we know animals have emotions just like humans. It's a proven fact.
Okay, anybody else?
Well, just one other point, just going off a bit, is I don't know if you've come across this sort of argument, Robert or Harry. The when he comes to saying, "Well, look, I am not going to accept anything which cannot be clearly established beyond any doubt at all."
Any doubt for Descartes.
Any doubt, quite so, yeah. And then he comes, "Well, there's no doubt about the fact that I exist because cogito ergo sum."
Cogito ergo sum.
Yeah, well, we're maybe blinded into that actually is begging the question, because in Latin the pronoun is integrated into the verb. So cogito, I think. But let's think of it in English. I think, therefore I am. Now, what does one wish to prove? That I am. Well, one actually starts the premise with I think. So that's a logical contradiction, and it doesn't become apparent in Latin because you don't see cogito ergo sum. You don't see the preposition, the premise starting with what you're trying to prove, namely the first person pronoun.
Yeah, I mean, there's a little bit more to say here. Actually, one of my philosophy professors was Willis Doney, and actually, when I was at Dartmouth, we went over to University of Edinburgh, and we had a special program there. But one of the things he said is that Descartes never said cogito ergo sum in the Latin. He does say je pense donc je suis in the Discourse on Method, and that's French. And of course, there you have the separate I and think. But I've heard, like Bertrand Russell said, that the most he could have deduced is there is a thought. When, yeah, maybe. So maybe you're saying that in order to, like to say, I think you have to separate the I from the thought. I'm not sure that's true, because if you're talking about conscious thought, if you start saying you have to have one thing like observe something else, you end up in a regress in a hurry. And one thing you want to do is try to avoid regresses. So if you collapse maybe the I, the ego, into the thought, then at least you're going to avoid a regress. And also, I think you're going to avoid the problem that you're just suggesting.
How do you define regress, please?
Repeating problem. You say one thing and it keeps repeating. Like if you like with the seeing, there's the I regress, the EYE regress. You look at the back of a retina, and actually Descartes even explicitly talks about this. You need another eye to see the retina, and then you need another eye to see the retina of that eye, and it keeps repeating, and you're not solving anything.
Okay, so like perhaps today's version of all of this, I think, therefore I am, is the video camera sees us, therefore we are.
Perhaps, yeah.
Because, like, I mean, that seems to be a whole lot more conclusive to me, because unless you want to postulate there's some sinister party fixing what the video camera is actually seeing and making it all up, and therefore we're not really here. It's all
that is similar to what Descartes had postulated. I don't really know how else he could express the idea without using the word I, though. I mean, he was into doubting everything, even his own existence, and he thought, well, what if my brain is in a vat and I'm caused to see all of these illusions? And so the only thing he could know for certain is that he was thinking. I'm thinking this. There's something tangibly there. So that's how I arrived at the idea, I guess.
Well, people who are diagnosed with schizophrenia can also make the same statement.
Anyone could. I mean, I've actually been diagnosed with schizophrenia.
Go on, get out of here. Well, I think this whole idea of the camera seeing us is a whole lot more concrete, at least for me.
Well, it is, but if you take into account that everything you're seeing is an illusion, which Descartes was postulating as a possibility, you know, the camera may be an illusion, like your physical body may be an illusion, your brain's in a vat, you're seeing all these illusions, but you know that you can think, you know.
Well, in other words,
But
we're
you
more
think you
sure
can
of the
think.
existence of our conscious mind than of the body. And I would agree with Descartes on that. Visual perception is incredibly indirect. So what we take as the distal object isn't. We're still in our mind, but there's still a distal object out there.
Well, the work of Rupert Sheldrake is kind of going towards that we connect to a consciousness, that consciousness is outside of our body and that we connect to it. That's his work on the morphogenic field. And I think there's something to that. Like, how does Mozart Beethoven, how is he able to wake up with a whole symphony in his mind and then have to rush to write it down?
Oh, I see what you're saying. But I think he only has parts. I don't think
Yeah,
he has the whole symphony.
it works all together. Downloads and
Yes.
uploads from us to this consciousness, and we get ideas from it, and I think that might explain how some inventions and discoveries are found around the same time, because it's being pulled from the major consciousness around us.
Cosmic consciousness, is that what you're talking about?
Well, the morphogenic field, Rupert Sheldrake that's what he calls it. But I think it reaches, he says it envelops the earth, and it's due to the biomass on the earth. I think it goes even further. I think it's part of the electric force, the electric fields that this consciousness arises from.
But whether that's true or not, the process is apparently that our unconscious is tapping into either that field that Sheldrake talks about, or our own system of cognition. So, in other words, in our sleep, we frequently are perhaps unconsciously resolving something which could result in maybe a solution the next morning. I've actually solved things, I think, in my sleep, or maybe in the case of Beethoven.
I think where he's coming from is because our brain waves match the Earth's human resonances. That's
wow.
Well, that's speculation. That's one theory, but we're talking about what actually happens. Conscious versus unconscious thinking.
It's too complicated for me. Let's come back to the space. My point is today to understand your opinion about space.
Can I ask one question just before, on Jerry mentioned Descartes doubting everything, but when I looked into this, he said he might try to doubt everything, but I saw no evidence. I could find no evidence in his writings that he did ever go through a process of doubting everything. And I think it's physically impossible to doubt everything.
I also agree.
Just go mad.
It's impossible.
You can just go mad if you doubt everything. You now have no basis on what to build up from.
I think
yeah. Well, I know what he says in the Meditations. He says, oh, he even postulates this evil genius who puts various realistic thoughts into his mind. And he says he can only eliminate that as a possibility if he can prove that God exists. And he has two very questionable proofs for the existence of God. The cosmological proof, which goes from the claim that he has this innate idea, an infinite innate idea of God in his mind and it must exist in reality. Or he has the ontological proof that God, by definition, has all possible perfections, including the perfection of existence, therefore God exists. But then he says in the sixth meditation that if God exists, among God's attributes is omnibenevolence, perfect goodness, and if he's perfectly good and also all powerful, he wouldn't allow this evil genius to exist. And he would have to have it be the case that Descartes' sense systems aren't misleading. And if they aren't misleading, then they will give accurate information about the physical world, about his environment. So he actually ends up trusting his sense systems, but he still makes a sharp distinction between a sensation and the cause of the sensation. The sensation itself is in this conscious mind. And he gives numerous examples, like with illusions and things. He gives, for example, looking at distant mountains, and they appear to be much smaller than they are, or they maybe appear purplish, whereas that's not the actual color of the leaves of the trees and things. So he definitely always distinguishes between a percept of a distal object and the distal object itself, but he still thinks that for practical purposes, we have good enough knowledge of what's going on in our surroundings. If we didn't, we'd always be bumping into things and having all sorts of problems.
I have a question. Why are we talking about Descartes? Like, for example, when you go back to the 1600s and thereabouts, are we talking about Descartes because he had a friend who has a printing machine, a book publisher, whereas the guy down the road didn't have such a friend, and so we don't know that he was asking the same questions and thinking the same things that Descartes was thinking. But Descartes had a friend who know how to make books.
I don't know the answer.
Well, it's just a question that occurred to me.
Well, I think the reason we're talking about Descartes, to answer the first part, is because he had a cosmology, and that cosmology is a precursor to modern science. And this is a cosmology discussion group. Does that
Yes,
help
let's
you?
talk about space, guys. Many times I'm trying
operational
to tell
definition.
you, let's come back to cosmology, to space, the very first session of today's.
Okay, to answer your
Guys, your
question,
opinion about the space. Tell me, what do you think about the space?
okay, to get on that, Descartes had the idea that space was some kind of a substance, not correct?
Yeah.
Is that not right?
That's right.
And he said that what really existed was extension, correct?
Race
And
extensive. Yeah.
and my thought when I hear that, my thought is, but isn't that really what atoms are? They're just space. They're empty nothings. That's the modern way we talk about atoms. So atoms are just empty space. So what is a material thing other than extension in space?
Well, there's particles that compose atoms.
Right. Well, but they're just things that are extended in space too, right?
Well, they exist in space, I would say.
Well, I would say that, those particles that make up an atom, they're joined together. They're not, there's no space in between them. If Ito's work is correct, with geometry and the way the atom builds itself, that using geometry, there is no room for space in between the proton and the neutron. So, I mean, if there's something that is between that makes the neutron and proton, then that makes the atom divisible, not indivisible. We know more nowadays than they did in the past, but it's also a good thing to know the context of history and understand where we're going and how and where we came from. Your talks on the historical aspect of science are great, Harry. I love them. They're amazing.
Okay, thank you. But I wanted to make this comment. It seems to me, though, that you're talking about electrons and neutrons and protons. Aren't they just empty things in space, too? Aren't they just extension?
Well, free electrons, free protons, and free neutrons, yes, they're out in space. They're floating around doing their thing. But when they consist of, when they get together, they make an atom. Granted, there's space between the nucleus and electrons. On their scale, it's a vast distance between the two, but on our scale, it's not that vast.
But what is the space between nucleons? What is it? Your name, there is no space between particles. And what do you mean? There is no space. Please give me definition, your definition of space.
My definition of space, it's
Yes.
a place where nothing exists.
Yes, you're an adherent of the void space conception.
Yeah.
That's my point that I was trying to get at in my talk, which is the these different ideas about what space is. There's really not an agreement.
Yeah.
But as regards
there's a lot
something
of thoughts
occupying space, you didn't mention these paradoxes which arise, Harry. I think Zeno's paradox. For example, if you have something, whether it's an atom or whether it's an extended material object occupying a place in space, one of the paradoxes says it cannot move because in order to move, it must move either in the space that it occupies or in the space that it doesn't occupy. Now, it cannot move in the space that it occupies because it already occupies that space. And it cannot move in the space it doesn't occupy because it doesn't occupy that space. Ergo, it cannot move.
Well, that's the same thing when I'm driving in my
go,
Ford Flex.
I would say
I've got elbow room.
that space.
Okay,
Sorry,
we
what's
have
that?
boy, that really stimulated some stuff.
Yeah, exactly.
Well,
Two
I was
guys
just
speaking
saying
at once.
when I'm driving in my Ford Flex, I got lots of space to move my elbows around. That means there's nothing there.
There's nothing
That
according
paradox.
to your definition of
In that
nothing
area.
that would interfere with your motion.
Yeah.
By nothing is you mean there's nothing that interferes with you.
Well, that can go all the way down to the
But
atomic where there's
if you took
nothing there.
away the windshield, you'd have a big problem.
See, the paradox is
Instead of
something to do
space,
with
we have right now
infinitesimal
It's good.
elements. How are you moving? Are you moving in an infinite number of infinitesimal increments,
Не работает.
or is it a continuous system?
Okay, now we have silence.
Sorry, was that question to me?
To all of you, really. I'm saying that the paradox really, I think, is related to our description of anything, whether it's made up of an infinite number of infinitesimal elements, or whether it's a continuous object. And the same thing with regard to moving the object. One of the other paradoxes is the famous one of the hare and the tortoise. And the tortoise is given a nod. He's given an amount by which he an advantage, but and when he's moved from that position to somebody else, well, will say the hare or Zeno, who's a very fast runner, when he's at the place where the tortoise started, because he's given an advantage, well, the tortoise has moved on another little bit, and when he reaches that other little bit, well, the tortoise has moved on another little bit, so he can never reach him. It's a question of these infinitesimal limits.
Right. I think that the point I was getting at when I was giving my presentation, I mentioned about the points. I think the problem has to do with the infinitesimals. And so you could think of everything as being divided. I can divide the hour into seconds, the seconds hour into minutes, the minutes into seconds, and then you can divide the seconds down and you can keep dividing. So for every size of a increment of time that you can imagine, you can always divide it in half or into other pieces. So that implies that time has infinitesimal number of parts. And so space has an infinitesimal number of points. But using this approach leads you to the paradoxes that you just talked about.
You mean an
So,
infinite number of points?
well, I think the issue is that Robert brought that up where he was talking about infinity. He said Descartes didn't believe in infinity. He referred to it as the indefinite.
Yeah.
Well, I'm checking the vocabulary. An infinitesimal number of points would be very, very few points. Oh, almost 0 points.
Well, that just means that I can
points,
not stop. If the infinitesimal means I can divide it in infinitely number of times. I can just keep dividing it into pieces forever.
And you talked about an infinitesimal number of points.
Now that means I can divide anything is an infinite number of times. The action of dividing is done infinite number of times.
Okay, but that's not actually what the phrase says. It says that there's next to 0 points. So what you really want to say is that there's an infinite number of points, I believe. It's vocabulary, that's all.
But points have no size.
At least according to Euclid.
Well, I mentioned earlier maybe the unfortunate forgetting of Fermat's contributions. He was one of the greatest mathematicians, actually, of his age. But and whether Descartes had a better press or more friends with printing presses or whatever. But even with the Newton business and Leibniz, it appears that Newton's teacher in Cambridge, one Isaac Barrow, actually gave Newton the first conception of getting the slope of a tangent by getting a chord between 2 points, which are a finite distance apart, and then diminishing that distance via infinitesimal points infinitely, and in the limit getting the slope of the tangent. So it appears that actually Isaac Barrow had the first idea of getting the differential calculus by evaluating the slope of a chord in the limit to be the tangent where the 2 points coincide.
So Isaac Barrow actually invented calculus.
Well, that might be a bit too hard to say, but yeah, you could actually argue that to a certain extent. See,
yeah,
nothing is new under the sun, I suppose, Harry.
Yeah. Well,
I've had this. Okay, go ahead, Bob.
Yeah, even Newton said that he stood on the shoulders of giants. So I don't think he would deny any of this, that he was building on the work of others.
Okay, we have 10 minutes. If you're interested, I'll give you my thoughts on this issue of the calculus. And that is that there's this theorem in electrical engineering, Nyquist theorem. And the Nyquist theorem says that you don't have to, all you have to do is divide it up into sufficiently small parts to represent a curve. You don't have to divide it into infinitesimally small parts. Okay, so you capture the information in a signal. Okay, and this is the basis of digital communications. You don't have to infinitely divide the signal into an infinite number of points. You only need a sufficient number of points. And he gives a theorem that says this is how you determine how many bits that you need to describe a signal in time. So you can describe physics in terms of quantized parts. So in other words, you don't have to have an infinitely continuous description. You can have it only in terms of quantized parts. Do you understand that? That's a very,
I
this is
understand.
a,
It's absolutely right. My point. You don't need it to go. There is some minimum size, I told many times in my model, and you cannot go down. You have some absolute dimension size, and that's it, simple like this. I'm asking you the questions, guy. Very important question for me. Space is infinite or finite? Let me answer this question, please. What do you mean when you're talking about space? It's infinite or finite?
Are you asking, Vladimir, or are you going to give your conception?
My conception finite, no doubts about it.
You say it's
Because
finite.
for infinite, I don't know, you can use only geometry. You cannot tell anything about infinite space at all, with infinite matter, with infinite number of points and all this stuff. Infinite, the most important part of space, it's bullshit for us.
One might then ask, where does it end?
Yes.
Okay, there is no end, guys. In my model, let me tell you, but that's why I have my patience, and now I want to tell you, I have a finite, but without space. Hypersphere. Hypersphere is the main point of my model. This is a space, hypersphere. You can move along this hypersphere for absolute long time, whatever you need, and never you will see the border. There is a finite space, there is a finite number of particles, there is everything finite. The main problem in physics that calculus, mathematicians, they physics. Harry, you're absolutely right. Newton, he talked about the small points, small sizes. That's it enough to define the infinite space, infinite velocity. How you then infinite velocity? Finite velocity, you have some small size distance, small size of time. Divide one by one, you have your infinite, and it's enough for us to define velocity. All these problems in physics and what we talk today about, it's with calculus, with mathematics, with geometry, with infinite space and all this stuff. That's why there is no physics behind of all these talks around. Physics, when you have something finite, you don't have border, yes, but you can move. One more time, you have your three-dimensional sphere. You can move along this sphere as long as you want, but it doesn't mean that infinite. It's finite. This is my point and my model point. That's why all this in philosophy, geometry this, geometry that, infinite small, infinite big and finite, and so on and so on. It's all mathematics, but we are physicists. And let's come back to cosmology. Cosmology group. We talked about everything today, but we didn't talk about the space.
What's on the outside of the sphere,
gave
though?
us very good theory, very good history of space, of different views, and I want to know your opinion because so many variations, and I didn't hear any voice of you about space.
What's
Please
on the
tell me
outside?
yeah.
space.
Vladimir, what's on the outside of the sphere, though?
The sphere is space. That's just
No,
a
it is
way
the
of
main
talking
point,
about it.
guys. Outside of space, there is no outside space. There is a sphere. This is a
So
space.
he's asking, what's your opinion, Harry? You gave the presentation on space. Do you have an opinion on the infinity of space or otherwise?
Well, okay, that's I didn't say anything about that. My point was that it depends on your geometry that you're using to make a measurement. So it's kind of like what Bob was talking about an infinite regress, which is you have to know what space is before you can measure it, and you have to be able to measure it before you can say what it is. So that's to me is the problem. The problem is that you need a geometry to make a measurement of space, but you can't measure space unless you have an assumption about what the geometry is. And so what Vladimir is talking about is, well, he says that there's a geometric model of space. His cosmology assumes a geometry of space as part of his model. Okay. And that is based on the assumption that space is finite. So his geometric model of space, the infinite cosmos of the universe, is that it's finite. And we don't get into this mathematical problem of infinities. Space goes on forever. We can infinitely divide space into parts.
Well, I would say that like if there's a theoretical line, like a straight line, that it would go on indefinitely. It would go on to infinity. I mean, why would there be a curvature? Why would it stay contained within a bubble?
Well, you have to ask, well, that's Vladimir's thinking about what physics is. And Vladimir's view, I think he has an idea in his model, his world universe model. He has an idea of physics, and that's incorporated in the model. And so Vladimir likes finiteness. What you described is Euclidean, a Euclidean concept that has within it the mathematical idea of infinity. So the Euclidean idea would be that there's no infinity means there's always a number bigger than any number that you can conceive. And so it just goes on and on and on forever.
Yes.
Right?
Yes.
That's a mathematical model. That's a math model. Okay. That's not necessarily a physics model.
Listen, on the contrary, it's a killer of physics. Please, let's stop be mathematicians, guys. Be physicists. Think about, physics, not mathematics, because I don't understand what does it mean expansion of infinite space. What does it mean expansion? You
I
have
don't
so
agree with
many
expansion either.
nothingness.
No,
Doesn't mean
we're not talking about
nothing.
expansion. We're just saying in terms of ordinary Euclidean concepts, there's
Euclidean,
no reason
it's
why the thing should
infinite.
be finite any more than you might postulate. Well, we can have a continuous curve which has only one surface. You have a width of paper. So that's impossible in Euclidean geometry. But if you twist it around and make a Mobius strip, you've actually made that. So you've changed the geometry. So in a way, with respect, I would say that you're changing the geometry as
No,
your basis.
hypersphere, it's a geometry. It's a four manifold space. Everybody knows it. I'm not changing anything. I apply physics to
All
the
right.
real
Okay.
world.
All right. We're gonna stop here. I'm not sure we can resolve this. I just wanted to give an introduction to what the controversies are, and we can
Yes. And we
argue
talked
about
about
this.
everything except your introduction. This is my main point. We wasted time on some other issues instead of talking about what does it mean space for us? What's the difference between mathematics and physics and so on and so on, guys. I'm a little bit frustrated today about talking about everything except what is the most important for today's session.
All right, we're
I
gonna
thought
have
it
to
was all
stop
interesting.
here. Maybe we can talk about that in the future